This presentation will provide advice for routine HPLC analysis. Today, I'll be talking about abnormal peak shape, particularly the effect of the sample solvent, mobile phase, column temperature and detector response. First of all, I will discuss the deterioration of peak shape due to the effect of sample solvent. We are analyzing benzoic acid, sorbic acid, and methylparaben in reversed phase mode. The acetonitrile concentration in the mobile phase composition is 25%. The chromatogram on the left of this slide is obtained by injecting these three compounds as a sample prepared using 25% acetonitrile aqueous solution as the sample solvent, which has the same acetonitrile concentration as the mobile phase. The chromatogram on the right is obtained by injecting the same sample but prepared with 100% acetonitrile as the sample solvent. Comparing the two chromatograms, the peak height on the right side is smaller. A closer look reveals that the peak widths of all three peaks are larger than those in the chromatogram on the left. This difference can be attributed to the change in composition of the sample solvent, which is the only difference in the two analyses. In addition to the differences in sample solvent composition shown on the previous slide, also injection volume can have a serious effect on peak shape. In general, peak shape deterioration tends to be greater when the injection volume is increased. What is the mechanism of this peak deterioration? Here, the effect of the sample solvent is explained using reversed phase mode in which a water and methanol mixture is used as the mobile phase. In the case of the methanol solvent shown on the left, the eluting power of the sample solvent itself is larger than that of the mobile phase. As this band moves through the column without any interaction to the stationary phase, a portion of sample compounds are pulled by the solvent band due to its larger eluting power, resulting in the sample band broadening. It interacts with the sample components and pulls some of the component molecules with it, causing diffusion of the sample band. In contrast, when the sample solvent is water as shown on the right, the elution power of the sample solvent is less than that of the mobile phase, so the sample band broadening caused by the eluting power of the sample solvent is completely suppressed. As a result, sharp peak shape derived from the narrow sample band is obtained. Let's look at the actual effect of the sample solvent on peak shape deterioration. The figure on the left shows the relationship between the injection volume and the number of theoretical plates when analyzing caffeine solutions of same concentration in reversed phase mode using a mobile phase of 70% of water and 30% of methanol. The vertical axis shows the number of theoretical plates calculated using the equation on the bottom right, considering 4 sigma as the width near the baseline of the peak and retention time. The horizontal axis shows the injection volume in logarithmic scale. 3 types of solvent are compared: methanol, a water-methanol mixture with the same composition as the mobile phase, and water. The column size is rather large, 6 mm ID. In both methanol and water-methanol mixture, the plate number of 12,000 with a 1L injection is decreased rapidly with the increase of injection volume. In the case of methanol solvent, the theoretical plate number is about 3,000 with a 20L injection. Even in the case of a water-methanol mixture with the same composition as the mobile phase, the theoretical plate number is decreased to about 9,000 using a 100L injection, which may be excessive considering the column internal diameter. These phenomena are peak deterioration due to solvent effect. Large injection volume means large sample band at the column entrance, resulting in large band broadening, even when the eluting power of the sample solvent is equivalent to that of the mobile phase. In contrast, when the sample solvent is water, increasing the injection volume slightly improves the plate number. This results from the fact that when a large amount of sample is injected into the column with the diluent having lower eluting power than that of the mobile phase, the sample compound is concentrated at the column inlet, as if it was injected into the column in a smaller injection volume. These results indicate that, as a general rule, it is important to prepare a high concentration sample with a solvent that has a weaker eluting power than that of the mobile phase, and to inject with the smallest possible injection volume. This slide shows a chromatogram comparison of the solvent effect of different injection volumes. The analytical conditions are the same as in the previous slide, with a mobile phase of 70% of water and 30% of methanol. The sample is caffeine, and the sample solvent is methanol, which has larger eluting power than that of the mobile phase. The injection volume is reduced from the top to the bottom, 100 ul, 50 ul, and 10 ul. However, the caffeine concentration is increased twofold and tenfold compared to the chromatogram above in order to check the effect of only injection volume while keeping the same sample loading amount. For the 100 ul injection, which has a large solvent effect, elution begins much earlier than the peak top, showing that the caffeine is being pulled by the methanol band passing quickly through column with little interaction with the stationary phase. Thereafter, the so-called leading tendency, which is a rolling hill-like elution continuing until around the peak top, is extremely apparent. When the injection volume is reduced to 50 ul, a similar leading trend is observed, but the starting position of elution is much later than in the case of the 100 ul injection. If the injection volume is further reduced to 1/10, a normal peak shape is obtained. This indicates that not only the type of sample solvent but also the injection volume should be reduced to obtain acceptable able peak shape. This slide shows the significant difference in peak shape depending on buffer capacity in the mobile phase. The chromatogram on the left shows the analysis of 3 compounds, benzoic acid, sorbic acid, and methylparaben, using a mixture of pH 4.5 citric acid buffer and acetonitrile as the mobile phase. All 3 compounds are separated with excellent peak shapes. On the other hand, the chromatogram on the right is obtained using the same pH 4.5, but phosphate buffer. In this case, the peak shape of benzoic acid is greatly deteriorated. Upon closer inspection, the sorbic acid peak is much smaller, and the peak width is wider. The methylparaben peak seems to be same as that in the left chromatogram. These phenomena seem to be due to the difference in the types of pH 4.5 buffer solution, whether it was citrate buffer or phosphate buffer. Benzoic acid and sorbic acid have carboxyl groups, and their dissociation state changes significantly around pH 4.5, which is the same value as the mobile phase pH. The pH at which the dissociated and undissociated of acidic compounds are exactly equivalent is called pKa. And the pKa of benzoic acid is 4.2, sorbic acid is 4.8, and methylparaben is 8.5. At pH 4.5 for this chromatogram, the majority of the benzoic acid molecules are dissociated and have monovalent negative charge. Less than half of the sorbic acid molecules are dissociated, and in the case of methylparaben, most of the molecules are undissociated. If the mobile phase does not have the buffering capacity to maintain a constant pH when analyzing under above-mentioned condition, the secondary electrostatic interaction between the surface of packing material and the ionized compound cannot be kept constant, and the peak shape may be deteriorated. This is more pronounced in case of benzoic acid, which has larger degree of dissociation than sorbic acid. Undissociated methylparaben is hardly affected. This corresponds to the case of phosphate buffer on the right. In other words, this chromatogram shows that phosphate buffer has no buffering capacity near pH 4.5. This is because the 2 of the 3 pKas of phosphoric acid are around 2 and 7, and phosphate does not exhibit buffering capacity in the pH range away from each pKa. In contrast, since citric acid has a pKa of around 4.7, it exhibits sufficient buffering capacity at pH 4.5 to keep the dissociation state of the compound constant, which is thought to result in little deterioration of the peak shape. Thus, when analyzing a sample compound in a charged state in reversed phase mode, it is necessary to select a buffer solution that exhibits buffering capacity at the desired mobile phase pH to deal with peak shape deterioration. Next, I will talk about the deterioration of peak shape due to temperature gradients along the column. HPLC columns are usually stored in an oven. The typical oven temperature is 40 degrees Celsius. If the room temperature is 25 degrees Celsius, there is a temperature difference of 15 degrees Celsius. If the room temperature and the temperature of the mobile phase in the mobile phase bottle are equal, the temperature of the mobile phase before entering the oven is 25 degrees Celsius, so the column temperature near the inlet is lower than that near the outlet, resulting in an uneven temperature distribution along the column axis. In addition, Since the high temperature of the oven is transmitted from the column wall to the inside of the column, the area close to the wall can be considered warmer compared to the center of the column, where the distance from the wall is larger. In other words, temperature distribution also occurs in the radial direction of the column cross-section. In the axial temperature distribution along the column length, molecular motion is not so active near the inlet where the temperature is lower. Therefore, mass transfer is slow, column efficiency is poor, and sample bands tend to be broadened. The temperature distribution in the radial direction has a significant effect on the peak shape deterioration. Molecular motion is accelerated in the high temperature zone near the column wall, resulting in a higher mass transfer rate and a faster sample band passing along the column axis. In contrast, in the center of the column, where the temperature is lower, mass transfer is slower and the passing speed of sample band is lower, resulting in a large sample band broadening due to curvature of the sample band, as shown in the lower part of the figure, and causing the peak shape deterioration. As a countermeasure, a preheating coil can be installed to heat the mobile phase temperature in advance to reduce the difference to the column temperature. This slide shows the improvement in peak shape that can be achieved by using a preheating coil. In the example, the column oven is set to 50 degrees Celsius, the column is short, 50 mm long, and linear velocity of mobile phase is relatively large with 1 milliliter per minute on the left. The mobile phase passes through the column before the temperature distribution in the axial direction of the column reaches equilibrium, resulting in peak broadening, while the peak shape is clearly improved in the right chromatogram with a preheating coil in place. In addition, considering heat conductivity, a preheater made of stainless steel, not PEEK, is considered more effective. To reduce sample band broadening, a preheating coil may be mounted upstream of the sample injector, but if the internal volume of the auto-sampler is large, the mobile phase may be cooled again, reducing the effect of preheating. If the preheater is installed just before the column in the oven, there is no such concern, but since the sample passes through the coil, it directly becomes the external column dispersion volume and induces band broadening. The appropriate position of a preheater should be determined by closely observing the resulting peak shape. Peak shape deterioration can be caused by detector settings as well. This slide shows how the response setting of a UV detector can affect the peak shape. This parameter setting adjusts the noise reduction function by smoothing. As a concrete description, the parameter of response indicates the length of the interval for taking the moving average of the UV detector's output signal. During the interval, observed signal variation is divided by the length of the interval to obtain the average variation. Then the value is output as the first point of the interval. Following second interval starts from the second point, which is just after the first point, consequently almost all the second interval is overlapped on the first interval and calculated value is output as the second data point. The length of the interval and data point resolution have no concern. When the signal variation is identical, a short interval means large output, as is shown here. Twofold longer response time setting does not always mean a half of peak height due to employing a special weighting method for the average calculation. A short response time setting means a short interval, resulting in a large average of signal variation. So, the peak height becomes large, but the noise level becomes large as well. In contrast, a long response time means a long averaging interval, resulting in small average of signal variation. So, the peak height and the noise level become small. However, the number of the intervals affected by the same signal variation is increased and the peak tends to be broadened. Therefore, in ultra-high-speed analysis, the short response time should be set to obtain a sharp peak considering separation priority. In high-sensitivity analysis, the long response time should be set because the decrease in noise is generally larger than that in peak height. There is a similar parameter setting, called sampling rate, which should be set to the same value as the response generally. In the next session I will look at baseline fluctuations and problems in reproducibility. Thank you for your attention.